Hello everyone. In this video, we will cover another fractional age assumption, the constant force of mortality assumption. As the name suggested, between integral age, the force of mortality is a constant. That is, for integer x, where s is between 0 and 1, then mu x plus s equals a constant. I denote this as mu x asterisk, or simply I will say that mu x star. By definition, px equals e to the negative of the integral of the force of mortality, mu x plus s, where s integrate from 0 to 1. And mu x plus s is a constant mu x star. And we get px equals e to the negative mu x star. Given px, we simply take the negative of the natural log of this, and then we get the constant force of mortality between that integral ages, okay, between age x and age x plus 1. SPX, by definition, again, e to the negative of the integral of the force of mortality dt, where t integrate from 0 and s. And we get e to the negative of mu x star raised to the power s. And the expression in the bracket is simply px. We get px raised to the power s. That is, between the two integral ages, the survival probability SPX equals the 1-year survival probability at age x px raised to the power of the duration, which is s. In terms of the life table functions, the L's, by definition, Lx plus s is Lx times SPX. And we have SPX as px raised to the power s. And we can write px as Lx plus 1 over Lx. We get this expression. If you want to do further simplification, we have Lx plus s equals Lx raised to the power 1 minus s times Lx plus 1 raised to the power s. Moreover, for s plus t, which is between 0 and 1, and s plus t are all greater than 0, then the survival probability SPX plus t, all right, this is still between two integral ages, okay, between ages x and x plus 1, because s plus t is less than 1. The force of mortality is a constant at mu x star. Therefore, SPX plus t equals e to the negative of the integral of mu x star, and say dy, where y integrate from 0 to s. And we get a similar expression, or the same expression as SPX, which is px raised to the power s. That is, as long as you are finding the survival probability between the same two integral ages, the expression is the same as taking the 1-year survival probability at age x and then raised to the power of the duration. That is, px raised to the power s. All right. So under the constant force of mortality assumption, we have the expression for SPX, and SQX is simply 1 minus the expression px raised to the power s. And the force of mortality, a constant, equals negative of the lateral log of px. And we have the expression for Lx plus s. And also we have the expression for SPX plus t, which is the same as SPX if x plus t is between 0 and 1. Let's move on to an example. Given that Q80 is 0.04 and Q81 is 0.05, calculate these four quantities assuming a constant force of mortality over each year of age. The first quantity, 0.4 Q80. We have 1 minus 0.4 P80, and then recall that SPX equals PX raised to the power S if S is less than 1. So 0.4 P80, we take P80 and then raise to the power 0.4. We get 0.0162. The next quantity, 0.65 P81. This is between the two integral ages, 81 and 82, and S is 0.65. So this is P81 raised to the power, the duration is 0.65. P81 is 1 minus 0.05, and then we get 0.9672. The third quantity, 0.6 Q80.1. The individual is currently at age 80.1, and then the duration is 0.6. So this is the probability that this individual cannot survive beyond age 80.7. The whole duration is between age 80 and age 81. We can still adopt this expression. The P 0.6 P80.1 equals P of 80 raised to the power 0.6. And then we get 0.0242. The last quantity, 0.4 bar Q80. An individual at age 80 can survive beyond age 80.4, but cannot survive or cannot reach 81.4. The first term, 0.4 P80, we can adopt the expression, which is P80 raised to the power 0.4. And then the second quantity, 1.4 P80, we can factor into P80 times 0.4 P81 and apply the expression, which is P81 raised to the power 0.4. And then substitute P80 and P81, we get 0.0433. All right, let's move on to the last case. Here we have x and t are integers, and x is between 0 and 1. We want to get an expression for t plus spx. Factor that tpx times spx plus t. And x plus t is an integer. And spx plus t is simply p of x plus t raised to the power s. And this equals this expression. Tpx times px plus t raised to the power s. And in terms of the L's, we have this expression. Let's take a look at an example. Given the mortality table, calculate 2.7 P79.6. Assume a constant force of mortality over each year of age. Factor this P's into 0.4 P79.6 times 2.3 P80. I just want to get the integral age at 80. So I split it into 0.4 and 2.3 in terms of the duration of 2.7 years. All right, apply the expression. This can be further factored into 0.4p79.6 times 2p80 and then times 0.3p82. The first term, which is p79 raised to the power 0.4, and then the last term, which is p82 raised to the power 0.3. We can get all the values of the p's from the live table. And then we can get the answer, 0.8581. All right, that's it for today's video. Thank you for watching. In the next video, we will be getting into an example involving a live table. Thank you and see you in the next video.